Okay, welcome everyone to week 7. So I'm your lecturer for topology, and topology is really a beautiful subject. So if you don't like it after week 12 or week 13 or whatever, then I really messed up. So whenever I'm too fast or whenever you think it's not fun, just stop me, ask questions, I want remarks and whatever. So usually the idea is I have kind of plenty of slides, one per week, so you can all find them already online on net. And if I really make it to the end without rushing, you have kind of messed up because you're supposed to slow me down. So that's kind of the game. So I'm trying to sell to you topology, which is really one of my favorite topics of all time. So it really turns me on, yeah. So topology is really amazing. And the game is that I would like you to love it in the end as well. So that's the game we are trying to play. Before we really get started, so today I'm kind of sketching a little bit what is the idea of topology. So there's essentially the only takeaway message in the first part is what are we going to do in the next few weeks, and why is this an exciting new idea? So if you really think about topology, and I give you some details and some examples in a second, but topology as a field of mathematics is just ridiculously new in some sense. So it originated about 100 to 150 years ago, and you might say, no, that's a long time, but if you compare to the more classical fields like geometry or number theory. So number theory, there were carvings in bones that people found were like 10,000 years ago. Humans were counting prime numbers. So number theory is super old, 10,000 years plus, and topology 100 years. And it was so unbelievably successful. It's really a kind of new idea that I'm going to sell you. It's very different from geometry itself. So geometry, maybe the first 6 weeks, if I would like to summarize them in one sentence, and it is like you're doing operations on vectors like rotations, stretching, or affine transformations or something, and it's very much coordinate based. You write down matrices, you write down vectors and coordinates and do operations on them, and topology is exactly the opposite. So eventually I would like you to forget about coordinates altogether, and we are just looking at the combinatorics of certain types of spaces. It's kind of a 180-degree turn compared to classical geometry. And maybe that's why it is so successful. So topology is one of the most applicable fields of math. Keep in mind that it's fairly new for mathematics, like 100 years or so. So it's really unbelievably great. And again, I said again, my game here is to convince you that topology is absolutely fantastic, and you should actually love it. So I love it. Hopefully you will love it as well. Some technicalities here. So I'm happy. So I have a Zoom appointments every Monday. So if you want to come, or just much easier, just write me an email. An informal email is totally fine. I'm very easy. Just write me an email if you have questions, or post something on that and I will answer it, or whatever. But really the point is, if you have any remarks, anything, just let me know. So last year, when I gave this lecture, I will have lots of very beautiful pictures here. And I was playing around with colors and pulling whatever red strings to the left or something. And after week 10 or week 11, one of the students came to me and said, oh, I actually can't see red. And I felt really bad because I was talking in the lecture about now pull the red string or take the red surface and do something with it. So really anything, just please let me know. We are all here to improve together. Yeah, so you can always just write me an email. Completely informal is completely fine. So I don't need any kind of horrifics or anything, just an informal email, and we are good to go. Okay, otherwise the rules stay the same. So whatever you've seen in the first 6 weeks will also apply in topology. So I will now outline topology, hoping to convince you that it's really beautiful. So right now in the first outline, before we go to the real math if you want, there's not really anything to understand. So just sit back and relax. And I'm going to explain what you're going to see in the next 6 or 7 weeks, roughly. Okay, so really topology is the study of properties of spaces that are preserved under continuous deformations. So here's a space. I will pull it up for you immediately. There you go. And topology, so for topologists, what you see here, those two curves or any curve in between, they're all the same spaces. So we study spaces up to continuous deformations. We can pull this string to the bottom. And for topologists, this is really just exactly the same object, as we will see. And note that this is completely coordinate free. So if you write it down in coordinates, this curve is clearly different from this curve or for anything in between. But for a topologist, these two spaces and like of the process of deforming them is all the same. And that's the essence of topology, the process of understanding spaces if we ignore specific coordinates of the space. We really want to focus on the intrinsic properties of the space. And what makes the top curve and the bottom curve very similar? Well, they essentially just connect those 2 points. They just do it in a slightly different way, but the essence is they connect those 2 points. In that property, they are just non-distinguishable. And that's what we topologists do. We kind of pick certain properties, and we study spaces or equivalence classes of spaces up to those properties. I will show you another nice example. So here's another example. If you take a disk, and for topologists, that's the same as pulling the ends of the disk and bending it up into a cup until you can fill water inside, all the same space, but eventually something changes, and we are trying to understand this last change. So the ball itself is not the disk. At the very end, you kind of collapse the boundary to a point, and that's a non-continuous operation. Everything in between is kind of the same. We just take the space, we don't care about the coordinates, we pull it up even further, so you can really fill water inside right now, but eventually the property of the space changes. And all about topology is understanding those points of change of a space under continuous deformations. It's very different from geometry. Right? I don't care, as you've seen the picture just from the disk that was pulled up, I don't care about area or length or angles or anything. Really just the property of the space that I can obtain by deforming it. If I take it into my hand and think of it as being made out of Play-Doh or something, and I can just push it around, it will be the same space for topologists. We only care about the intrinsic properties of that space. And what was the same here? Well, they all had the nice boundary, right? They always had the nice boundary, and then there was something going on in between, except for the last step where the boundary collapsed to a point. And that was a different space topologically. So here's another one, just to make sure. You can always shrink a ball, for example, until it looks like a more classical space of geometry. And they're all the same, because we just shrink it without changing its internal property. But eventually, we'll hit some singularity somewhere, and the space will change. But everything you see here is the same space topologically. Think of it as being, I say it again, think of it as being made of Play-Doh, and you just squeeze it until it looks like a pyramid, and no problem. You could do this live, and if I would have some Play-Doh here, I could do this live for you. So it's very different from geometry. It's kind of a lot of fun. So we're playing a very, very different game, and it will be a nice ride. Okay, I have another one for you, and then we continue a little bit. So for a topologist, a cow is actually the same as a sphere, because you can just take the cow and turn it into a sphere, and you can just pull it around until it looks like a ball. So for a topologist, a cow and a ball are the same type of object, completely coordinate free, right? The cow has very different coordinates than the ball. That's what we're going to do. We're going to study properties of certain spaces under those types of deformations, where you could think of them as they're sitting in your hand and they're made out of clay or something, and you can pull it around without having any singularities like in the last picture where you collapse the boundary. And I will split it into 3 parts. So we're going to study one-dimensional objects. We're going to start with those today. They're called graphs. So these guys here are graphs. These ones are graphs. They're one-dimensional. I've just blown up the points. These are just points. And then there are lines connecting the points. That's a one-dimensional space. And we study those properties of those spaces as they are as one-dimensional spaces sitting around. We'll see what that means. And then what is the next step if you understand one dimensions? Well, you go to a two-dimensional space, and we will see two-dimensional spaces. So they are called surfaces, like a two-dimensional thing, like this one here, or the cow. The cow is the surface if you want. If you ignore the inner parts of the cow is the surface. And eventually, so the last topic will be something extremely fun. We'll take a piece of rope and put it in 3 space and see what we can do under continuous deformations by gluing the ends together of the rope. And we'll just go ahead. So 1 dimension, 2 dimension, and then kind of playing with what we have learned before. And these are kind of the outlines. So maybe the first 1.5 weeks will be on graphs, and like 2 or 3 weeks will be on surfaces, and the remaining will be on knots. And surprise, surprise, everything will appear in the final exam. Okay, so that's maybe not a big surprise. There will be a nice mixture between questions about those objects. Okay, and these are all topological objects. We study them in the sense of topology. So it will not matter how I draw my graph here. I will do that later. So whether I have the vertex labeled 6 up here, this was really bad. If I have the vertex labeled 6 up here, or whether I put it down here by just moving it down, it doesn't matter. It's the same object, because what counts is its intrinsic property, and the intrinsic property here is that 6 is connected to 4. And it doesn't change no matter where I put my little vertex. And we will deform the other spaces as well. It's really exactly this idea that you take them in your hand and you're deforming them, thinking of them as being made out of clay, and you pull them around, but you're not allowed to kind of cut your clay into 2 pieces. You're not allowed to have singularities. So you're not allowed to have non-continuous operations. So everything here, let me pull up this animation again. I just pull it, I pull it up, that's all fine. That's all still good, but eventually something crucially changes in the space. It will lose the property of having the blue circle. The blue circle will collapse to a point, and that's exactly this one step, which is kind of not allowed in. It's not a continuous deformation of the space. Okay. So that's topology. It's kind of the idea of topology is to study intrinsic properties of those spaces, right? So whether the number 5 is placed here or whether I place my number 5 like here, it doesn't matter, because the intrinsic property that 5 is connected to 1, 2, and 4 is still preserved no matter where I place my little node number 5. So the little circles here, the dots are called nodes or vertices. And that's an intrinsic property we'd like to study. I said again, it's very different from geometry, so I will never force you to write down any coordinates, but we'll rather play with the combinatorial intrinsic properties of those spaces. Right? So, and we really want to understand those 1-dimensional objects and the 2-dimensional objects. Eventually, topology studies any kind of dimensions, but higher dimensional spaces get a bit difficult to imagine. So we only do 1-dimensional and 2-dimensional objects. And again, I said again, we're allowed to wiggle and stretch them however we want, as long as we don't have non-continuous operation like tearing them apart. Right? So that's what we don't want to do. And what we'll see, kind of as a sketch how we do is the following idea, which is kind of really, really beautiful. So you're sitting in an analysis class, you're learning calculus, and calculus is really difficult. You have to solve crazy integrals or differential equations or whatever. And it turns out that arbitrary curves and surfaces are really kind of difficult to study. And it's somehow much better to find a combinatorial, a discrete way to study them. And the way this class will proceed is the following. We think of having one of those spaces, whatever, like a curve, and it goes up and down or whatever. It's very, very nice and wiggly, very difficult maybe, but we're allowed to turn it around. We're allowed to change it. And a nice way to change it is just turning it into something more discrete. So this is the same curve for a topologist in some sense, but it's somewhat a little bit easier to understand, right? Or zooming in a little bit more, you can add more points, still the same curve, but a bit easier to understand because it's now a discrete object. Everything is just made out of straight lines. So somehow we try to approximate our little spaces by something much easier, like approximating a sphere by a tetrahedron, or by a cube, which is a kind of easier to understand object than the sphere itself. And what we'll see is essentially, well, you take your square, right? We're not doing geometry. For a topologist, a square and a circle are the same. Right? Take your square, take it in your hand, and smooth out the edges, and you get a circle. Thinking of it being made out of clay. Or take your circle and make a little corners, and you get a square. We're not doing geometry. Squares the same as a circle for a topologist. And I will explain that more formally later. For right now, just sit down and relax, as I said. Same for the two-dimensional version. A cube is the same as a sphere. Just take the corners and smooth them out, or add corners to the sphere if you want to go the other way around. And this is kind of a little bit of a shocking type of idea, and maybe that's why topology took such a long time to be developed, right? We're not really studying the objects, but we are studying the objects up to they're made out of clay, and we are kind of want to play with the clay. We want to play with the Play-Doh and continuously deforming it. And we only care about the intrinsic property of those spaces. So what, for example, is an intrinsic property that this space and this space share? Well, they are hollow, right? So they enclose some air inside which can't get out. That's a property that those two spaces share. It's an intrinsic property which is preserved under my deformation from a cube into a sphere. And we are really interested in those type of properties and not so much into area or angles or all that difficult stuff that we are not going to touch at all. Right? That's intrinsic property. And we'll see more funny surfaces like my little swim ring here. I have this picture of the swim ring to remind you that this thing is also always supposed to be hollow. So this is hollow. There's air inside. So there's also air inside here. So what is the difference between those two spaces? They have both air inside. So are they actually the same or not? Well, right now we can't really tell. I only told you one property that is preserved. They have air inside, and both of them have air inside. Think of it as follows. I hope all of you agree that our Earth is like of this shape. But how would we check that right now, like locally here? Everything looks like very flat. So how can I check if I just being a little human living on the sphere? How can I check, like I'm standing at that point? How can I check that my Earth is a sphere? Why is it not this type of object? Huh? Locally, I somehow can't decide. And we are trying to develop techniques such that we can decide actually that the Earth is this type of shape and not the bottom type of shape. Right? But locally, I can't decide. Everything just looks flat anyway. So is it a sphere or is it a swim ring? I don't know. Really, locally, I can't decide. So there's some intrinsic change of properties going from one to the other. And topology is really about understanding those differences. And I don't really care how you draw it, whether you draw the sphere as a cube or as a sphere itself. Awesome. Well, let me show you another animation, the old joke, that for topologists, the little swim ring we just saw is the same as a coffee cup. So here, think of the coffee mug as being made out of clay, and you can continuously deform it. The only thing that kind of matters is that you have this little hole here, and you can continuously deform it until it looks like one of my swim rings, or some people call this other shape a donut, whatever you like. And people really love topology, so some people have a lot of time and just did that really live. So you can really deform one space into the other if you really think of your coffee mug as being made out of clay or Play-Doh or something. So they're really the same type of spaces. Really kind of extremely beautiful. And we're trying to understand, given one of those, how can we kind of decide which one it is, right? So we are playing this game that we are trying to decide what the Earth is. So which one is it? Is it one of those? Or is it a sphere or something more absurd? We can't tell right now. And we are about to learn in topology, how can we do this? It's kind of a very interesting idea. How can we actually tell the shape of, well, you might say, okay, we all know the shape of the Earth. Well, you just can check it if you fly to the moon, you can check that it's a sphere. But maybe you're more interested in something like the shape of the universe. So where would you go in order to check the shape of the universe? Outside of the universe and just try to observe what it is? So we need some way to decide what kind of space we see. So what is the shape of the universe? An excellent question. And topology kind of gives you tools to decide all of these questions. Okay, so that's my little wrap-up of topology. So topology is really about that a cow in the sphere or a human in the sphere are exactly the same type of objects if you think of them as being made out of clay, and we're trying to understand, so if you now have an object which is not the sphere, how can I actually tell whether it is not the sphere? And we're doing this using combinatorial methods. So we will never write down any form of coordinates. I think in the beginning I will write down a little bit of coordinates to kind of keep it, to slowly diverge from, converge from non-coordinates to coordinates, the other way around, from coordinates to non-coordinates. But eventually I would like you to never write down coordinates. I would like you to argue using what we learn and your intuition, essentially just by taking the spaces into your hand and doing it live, if you want. I will have plenty of more animations as we go along. Awesome. So this was kind of the first half of today, kind of what we are going to see. And now we are doing some real mathematics. Don't worry, we are not going to do real mathematics. We are going to do topology. Whatever. So I'm going to go to the first topic, which are graphs. And I will explain everything how you would see it in a lecture book, and then I will tell you that's not the good way of doing it, right? So I'm going to explain it in a certain way, and then I'm going to tell you that it was really shit what I did. Very strange way of doing it, but I want you to learn that sometimes the definition is really not what you should look at. And topology is the subject where the definition is not what you should look at. But it's more like the intuition and the properties you will see from those spaces. So we'll see now several kind of strange looking definitions, and then I will show you pictures, and I will always tell you to just look at the pictures and forget about the definitions. And that's the essence of topology. Never write down coordinates, right? Okay, so let's go start with coordinates. So a graph, formally speaking, is a pair of vertices, my little v's, and it's a bit boring if they're empty, so let's say it's not empty, and a pair of edges, the E set. And this is a multi-set. I will explain in a second what that means. Okay. And that's a graph. And now you wonder, what on earth does that have to do anything with what I just told you before? Again, I don't want you really to look at the definition, but let's look at an example. All right. So we could have something like 1, 2, 3. I just give those things names. So 1, 2, 3. And what I will do is I will write them down. 1. This was a really shitty one. Give me another try. 1, 2, 3. So the vertices are just, you should think of them as being 0-dimensional, just points, but I blow them up a little bit, otherwise you can't see what I'm doing. Okay, so I have 3 of them. So 1, 2, 3. This is my set V, my little points here. And now my E tells me where the 1-dimensional objects go, tells me where the edges go. 1, 1 just means I start at 1 and I end at 1. So 1, 1, I put a little edge here, and I put another one here. I have another one of them. And turns out I have another one of them, so I will put them here as well. And then I have an edge from 2 to 3, which is just this guy here. Okay? So the formal definition of the V and the E tells me the following type of information. I have some kind of set here of vertices hanging somewhere in my plane. Well, and the E is just a way to encode an edge, which always has a start and the end point, which is exactly what you see in that set. I have a little bit of a nicer picture, not drawn one. So here's another one. A, B, C, D. Let's draw it. AA, AB, AB, AC, AD. And maybe you can try to be faster than me if you want. So let me just draw an A here, and a B here, and a C here, and a D here. Okay, that was my set V. Just some bunch of points that I just blow up, as I said, in order to make them visible. And then I have an AA. So let me just color them. I have an AA. I have an AB. AB. I have another AB, maybe this color. I have another AB. I have an AC. There you go. And I have an AD. There you go. AD is my little, what is it, violet, purple, something like that. And that's how this abstract definition encodes actually the spaces we have seen before. And as we go along, actually very quickly, I would like you to forget, well, keep it in mind, maybe not forget it, but we really want to look at the combinatorial object that we will call a graph. So the graph abstractly is just the two sets V and E, but we really would like to think of it as an object where we have some vertices and they are connected by some connections. And you could think of this as, for example, as a street map. So A, B, C, D are some points here in Sydney, and the edges are the streets connecting them, for example. Or for the train system, right? A, B, C, D are train stations, and you have some, well, tracks connecting them. So that's kind of the idea. And we just want to formulate this mathematically. You could think of it as being a picture of the brain, a very pathetic brain in this case, but anyway. So we have the neurons here, and they're connected. So we could fire information between neurons. And that's the essence of a graph. And we just put it in this mathematical framework of the V and the E's. And so we do this here. I have it here formally on the slides. Let me say it again. It's not a good idea in topology to just work with the coordinates. So we never really work with those. Just keep it in mind that that's how you would formally write it down. But I would rather draw my little picture here, which hopefully makes now some sense and is a bit nicer than hand drawn. I have 3 vertices sticking around in the plane, and I connect them. Maybe I give them colors again. So let's say this one is this one. Yellow is maybe not the perfect color. Orange is this one. Blue is this one, and the green one is this one, right? And the difference why this E was called the multi-set on the previous slide is that I have allowed multiple entries, right? This one appeared 3 times, and I have 3 of them on my little graph here. And formally speaking, the thing I'm drawing is called a realization. And why is that the case? Because really, we want to study properties of spaces intrinsically. And intrinsically really means the only thing I see is I have a bunch of vertices which are connected by certain types of edges. But whether I draw them like here, or whether I draw them as follows, I have my little 1 here, and my little 2 here, my little 3 here, and let me use the same color code. So whether I draw them like this, well, for example, and the others, whatever, a loop here, and I had an orange loop which could go like this, and maybe a blue one which is just like this. These are the same type of objects because we only care about the intrinsic property. And the only thing we see intrinsically is that I have a vertex which has a certain number of things connecting them, right? And the bottom is the same as the top. And that's why I would call every such drawing a realization, because it's strictly speaking not the object itself. It's us drawing it so that you can imagine it a bit nicer. So those 2 things are the same. And we'll make that, they're the same, right? So the bottom one is encoded by exactly the same V and E as the top one. So this little word here, realization, as well as the difference between us drawing it or it as an abstract object. As an abstract object, I cannot tell the difference between the bottom and the top because I can only see what is connected to what. That's the only information I have in the abstract object of a graph. And note that this is not connected. So connected just means you can go from everywhere to everywhere. Okay, let's draw the next one. I already had it, but maybe this drawing is a bit nicer. So let's see whether we can give them colors. So AA is here, AB, and another AB. These are those 2 guys here. Maybe blue, we already have blue, maybe red. AC is this one here, and this greenish color here for the last one. And it doesn't really matter how I draw it, right? So again, this is just a realization, and I could have drawn the edge C somewhere here, the vertex C somewhere here, and it would be the same type of space. And this graph is connected. As you can see, you can go from everywhere to everywhere. And we just met the first intrinsic property of a graph, whether it's, for example, connected or not. Connected really just means I can go from everywhere to everywhere. Here I can't go from 2 to 1. And at the bottom I can go from A to B, from A to C, from A to D, but also from D to B via A, for example. That's an intrinsic property of the graph. In particular, we could see immediately that the 2 spaces are not the same. because there's one intrinsic property which they don't share, right? And we are studying spaces up to deformations, and they're just really different, for example. There's another way of seeing that they are different. They have a different number of edges, they have a different number of vertices. There's also another property to say that they are different. And this is the first, maybe not completely obvious, or whatever obvious means, maybe not completely obvious property of a graph, which is intrinsic. Sure, the graph is defined, I say it again, to be a collection of vertices and connections between them. So these are, of course, properties that stay invariant under our topological deformations, but maybe this one is not a completely obvious one. But since we can't tear things apart, the connectivity of a graph is an intrinsic property that stays fixed. And that's exactly what we want to do. We want to decide whether the surface we are on right now is a sphere or not. So we're looking for those non-trivial intrinsic properties that we can somewhat check that the sphere has, for example, and whatever, the swim ring doesn't. We're looking for those properties. And here's a first example of such a property. Okay. And I really allow everything. Like those guys here are called loops. These little guys here. And maybe this is a better color. If you have two or more connections between two vertices, they're called duplicate edges. Okay. Sometimes I will throw them out. That's why I highlight them here. But that's just the name. So let's go through the names again. The zero-dimensional things that have blown up are called vertices. The most crucial information are how they are connected, and the connections, the train tracks. The train stations are the vertices, the train tracks are the edges, and a loop is a little bit of a boring train track, so it gets a distinct name, and also we have duplicate edges here. Okay, and this is kind of really crucial, and I say it again. We are interested in the intrinsic properties of spaces. So we can't zoom out. We are standing here on our surface Earth. I can't just go to the moon and check how the Earth looks like. I'm just here stuck with my space. So I'm actually not allowed to really draw it. But we're still drawing it, of course, because it's much easier to visualize. But the graph itself is really just V and E, okay? Just as two sets. And not the drawing. The drawing is a realization. Again, please draw the graph. Always do that, but keep in mind that this is your way. Whenever you draw a graph, this is your way of imagining how the graph looks like. And it's not a universal way. Everyone would draw a slightly different graph. So let's say you are the lecturer, and you would have designed those graphs, then they might have looked a little bit different in the drawing. And that's why a drawing is not a universal way of doing it, but it's still very powerful. So I'm not saying forget about the drawing. I clearly say keep the drawing in mind, but they could look very different. So let's check whether these are actually all the same. So I claim here they're all the same. Well, they certainly have all four vertices, and they all have, well, let's count. So 1, 2, 3, 4, 5 edges. Therefore, it's so far good. A always has a loop. As you can see in all pictures, A has a loop, and AB has those parallel these duplicate edges. And A and C are perfectly, A and D are perfectly connected. A, D, and AC are perfectly connected in all of them. So actually, they're all the same graph. So this is equal to this one. This is equal to this one. This is equal to this one. And you get the point. And that's why a drawing is a little bit deceiving. So I showed you this one, but I could have showed you this one, or this one, or another one. So really, a graph is the abstract object, and we are studying it up to intrinsic properties of those spaces. Always keep that in mind, and at the same time, always draw the graph, okay? We are always drawing everything. But keep in mind that this is your way of doing it. It's not a universal way. Everyone will have a slightly different drawing. Everyone is slightly different. But the graph will stay the same. And now I show you more graphs, because life is about examples. So let's have a look at certain very specific graphs that are so important that I will give some symbols. Okay, the first one is what I call Pn, and n is a certain number, 1, 2, 3, 4, 5, 6. And I call them path graph or line graphs. And they're the following. So abstractly, they're just 1, 2, 3, 4, 5, 6 as the number of vertices. I have a drawing in a second, but I will also draw them here. So I have 1, I have 2, I have 3, all the way up to whatever n. Okay, I put them here, and my edges are always 1, 2, 2, 3, 3, 4, 4, 5. So what are my edges? Well, 1, 2, 1, 2, 2, 3, 3, 4, 4, 5, and so on. So it's a line, right? So that's why it's called a line graph. You can draw them in any way you want. So the name line graph is maybe slightly bit misleading. You could draw them in a very crazy way, but they really look like a line if you draw them in this way. And kind of the easiest graph you would come up with like immediately. So let's just do it. So if I just have 1, then my set E is empty because I have n minus 1 n at the end. So this is the first line. It's a very boring line. It's just one vertex. It's a line. It's one vertex. It's just the starting point of a line, if you want. And then we continue. Oops, that was one too far. 1 edge, 2 edges, 3 edges. Observe that there's always one vertex more than an edge. So the last one has 4 vertices and 3 edges. The next one would have 5 vertices and 4 edges. So that difference, vertices minus edges, is an intrinsic property in this case of this graph. You can distinguish the graphs by just having this count. So vertices minus edges, so this would be 1 here, and here you have 1 edge and 2 vertices. Here you have 2 edges and 3 vertices. Here you have 4 edges. I should be able to count. You have 3 edges and 4 vertices, and so on. You can distinguish them by looking at those two numbers. They're not the same. It's an intrinsic property of one of those graphs. And as I said, we are looking now at kind of standard graphs. So we give them some nice names. So here the Pn is a path graph. It will appear several times because it's kind of the easiest thing you can write down, right? It's fairly nicely ordered compared to something like this, which doesn't have a name. Okay, so this one's hopefully clear. And well, if you have a line, maybe you have a circle as well. So how does it work? Again, I label them C1, C2, C3, whatever, C512, and I do the same. I put a vertex, 1, 2, this was a really bad 2, 2, 3, and 4, and I will connect them now as follows, 1, 2, I start exactly the same way, 2, 3, 3, 4, but eventually I will go back to where I started, and that's why it's called a circle. So this is C4. Maybe I should write this next to here. This is C4. Right? So 4 vertices. And why is that not the space at the top? Why is it not a line? Well, this one has 4 vertices and 4 edges, while the top one here, for example, has 4 vertices and 3 edges. So there is an intrinsic property which is not satisfied, which is not preserved if you go from one to the other, so you will never be able to deform the top one into the bottom one, which is kind of visually clear, but we have found a better way of explaining that because we just count here instead of saying it's visually clear, which is a bit awake, of course. We found a better way of saying it. We just say the bottom one has 4 vertices and 4 edges, and the top one will never have the same number of vertices and edges. So C4 will never be on the list above for no n. Right? We'll use an intrinsic property to say that the Earth is not this shape, if you want, or the line graph is not this shape. Hope that was reasonably clear. And of course, I have a slightly nicer picture here. Note that the first one is a bit silly. So if you do the first one, you have 1, 1, so you get this little loop here on the first one. And again, let's do the count. So the number of vertices and the number of edges is always the same. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. So no graph on the bottom list can be deformed into anything on the top list and vice versa, because we found an intrinsic count to distinguish those objects, which is pretty cool, actually. It's a very easy argument, and we have actually a really good way of saying they're not the same. I say it again, you can of course somewhat eyeball that they are not the same, but there you go. There's an argument why they are not the same. Well, and these are kind of my first examples of graphs. That's what you would write down as first type of examples anyway, right? Maybe you write down a line, maybe you write down a circle. So they will reappear several times, so I give them the P and the C. This one is a bit more sophisticated, but it plays still a very important role in the field, so we'll just do it. And if you just look at the vertex set is easy. Yeah, let's just draw it. Okay, let's do n equals 4. So K4. So you just do 1, 2, 3, 4. 1, 2, 3, and 4. That was easy. But the edge set looks a bit like complicated. But what is it really saying is the following. So let's say I is 1. Then I can have j everything else. What does it mean? That means the following. So I is connected to 2, I is connected to 3, and I is connected to 1 is connected to 2, 1 is connected to 3, 1 is connected to 4. Right? Just look at the property. If my thing, okay, I've done that one. So now let's I to be 2. We have I equals 1. When I is 2, j needs to be bigger, so j can be 3 or 4. So we can draw in the next set of edges. There you go, 3 or 4. We're done with I equals 2. We're now going to I equals 3. Well, the only thing that is bigger than 3 is 4. So we add in another edge. And here we go. Another edge from 3 to 4. And that's why it's called the complete graph. Because now if you look at it, everything is connected to everything. That's essentially what it is. 1 is connected to everything. 2 is connected to everything else. 3 is connected to everything else. And 4 is connected to everything else. That's why it's called complete. You put as many edges as possible without creating any loops or duplicate ones. Just put everything. A very important family because it's kind of the put everything, right? So very generous. You can just give out everything to everyone. That's very good. And that's why we have them on our list as well. So here are they. Whoop, whoop. They get pretty complicated. Well, here 9 is connected to everything, so it has quite a few edges. And we can do the same count. So, well, the first one is just a vertex, fine. The second one has 1 edge and 2 vertices. So it actually was on our list before. So this one is P2. So P2 and K2 are actually the same type of graphs. So I'm not saying these lists are not intersecting. The next one looks like a circle, like a very strange circle. Well, but we are doing topology, so it is a circle. And indeed, if you do the count, it has 3 vertices and 3 edges. We have seen that one before. It was C3. And then it gets unique. And you can see that again on the number of edges. So this is C3. Because the next one has 4 vertices and how many edges? It has 6 edges. So it's not on any of the list. And then the number of edges just grows very, very fast, as you can see in the last picture. So this is C9. There's one more set of graphs, and this one is a bit, well, let's go through it again. This one is a bit weird, but it turns out to be very important. Okay, I would write down the first sequence of graphs. Okay, eventually we will write them down. Eventually we will write down the second sequence of graphs. Right? That's just what you would do. This one, well, if you really play around with this is just a very, very generous one. Eventually you will write it down as well. I agree that it's a bit more complicated than the other 2 families, but it's not so far off, right? So eventually you probably would write down this one as well, where everything is just connected to everything. The next one is a bit weird, and it kind of is a miracle a bit in that it turns up in the theory so often. So what we do now is the following. There's a word complete, and we'll do the following. And I really ignore now what I've written in E. I just draw the picture, and you're supposed, if you sit down, you will see that either I have a typo in E, or it works out as follows. So what we do is we write down 2 sets of vertices. Okay? So I have a red set, 1 to n. I have 2 numbers, n and m. A red set and let's say a blue set. Blue is good. Red and blue. I have a red set and a blue set, and I write them down. Okay? So here's my blue set, and here's my blue set. So here m is 2, and here m is 3. And I have my red set here. So here n is 2, and here n, oh, sorry. I have my red set here. Here n is 3. And the rule is to never draw an edge between the same color, but draw all possible edges between different colors. Okay? So at the top, 1 is connected to 1 prime, 2 prime, and 3 prime, and so is 2. But there's no connection between 1 and 2. Right? So no connections within the red component. The red component has no connections, and the blue component has no connections. But everything in between, you can put everything kind of in between. And that is why it's called the complete bipartite graph. So bipartite means exactly I have 2 colors, a red one and a blue one. And complete is just I put all edges that I can possibly put in between. The complete bipartite graphs. And we have 2 sets, the red set, the n indexed by n, and the blue set indexed by m. And I usually like to, but again, it's just a drawing. What I usually like to do is I like to put them as follows. I put my red set at the top. I put my blue set at the bottom. Here's my little blue set. And then I have whatever kind of edges going from top to bottom to connecting everything. So that's kind of a very sketchy picture of what those complete bipartite graphs are. Okay, so this one is a bit strange, but it turns out to be very important, so we give it a name. So this one was K, Kn for complete. So K for complete, not quite sure where that notation comes from, but K is usually used for complete here. And the K with 2 indices is the one with the red and the blue, so with the bipartite graphs. Awesome. One more thing, and then I'll let you go. Sometimes we want to do the following. Sometimes I want the following picture. Sometimes I think of having 2 train stations. But let's say the trains can only go in one direction. So drawing this picture for my 2 train stations, when the trains can only go in one direction, is kind of a bit weird, because I'm not keeping track of the direction, which is really, really crucial if you're designing train tracks. You should keep track of orientations. And that's why we put a little arrow here. So that's what I want to do, and we call those guys directed graphs. Everything gets a little direction, and I will show you in a second how that works. Okay. So let me go back here. Kind of the easiest setting. Train tracks and trains can go in both directions, so I don't need to draw any orientation. And these are called undirected graphs, or I will just say graphs. And these guys, trains now have a direction. Right? On a street, you can only go maybe in one direction instead of in 2. Sometimes that's the case, so you add a little orientation. So this little arrow is called an orientation of the edge. And how do we do that formally? Well, here we go. We have V and E, and we do it as follows. We, instead of set brackets, so let me go back. This is kind of exciting. You have never seen this before. Instead of set brackets, where's a good example? Instead of set brackets here, so a set bracket means 1, 2 is the same as 2, 1, so I can't tell which one is start and which one is end. And now I just write down a tuple, and the tuple has component 1 and component 2. And now I, for example, know, I will have the example here in a second, that this edge starts at 2 and ends at 3. Otherwise, it's the same type of information. And just add this extra information where something starts and where something ends. And I put it on the graph by just putting a little orientation here. So if I would have 3, 2 here, so let's say I would have 3, 2 instead of 2, 3, then my edge would go in this direction, right, for example. And that's how I can distinguish them. For loops, it doesn't matter, because loops start and end at the same point. But for all the others, it will. And this is just the directed version. It's just called a directed graph. So here's another example. Let's see whether we understand this example. So AA, okay, fine. AB and BA, right? So we have an edge AB, is this one that goes from A to B, and we have an edge BA, that is this one that goes from B to A. And then there's an edge AC and AD as before. So now we can keep track of the direction in which a train goes. And we call that a directed graph. It's kind of really the same idea. Okay, and that's what I wanted to do today. So thank you so much for coming. And keep in mind that what we're really studying are whether they come with orientations or not, but we study those things up to intrinsic properties. So I will always draw them because drawing is so much fun. But eventually, really what they are those abstract definitions. Okay, thank you very much.